Good day, everybody, and you're most welcome to today's CNPS Saturday session. At the CNPS, we are delighted to be able to introduce new ideas because, unfortunately, in the modern world, and maybe this is not something which is entirely new, but new ideas have received a fairly poor reception. Now, I have a quotation here from the philosopher John Locke, who, in his essay concerning human understanding, in the dedication, this was written in 1689, he says, new opinions are always suspected and usually opposed without any other reason but because they are not already common. So maybe this hesitation to entertain or even consider new opinions is not new. But we are breaking the mold, hopefully. And what we're hoping to do, perhaps today, and perhaps for succeeding 2 Saturdays, is have some work which has been done by John Hodge. Now, John Hodge has presented to us in the past, not terribly long ago, actually. But in my discussions with him over the preceding weeks, he has suggested that we have 3 videos. The first one is basically an introduction to his Scalar Theory of everything, dealing with cosmology. The abbreviation Scalar Theory of everything is STOE. And that is described by John as it's a model which is an alternative to and is more complete than relativity and the Big Bang model. So now, as I say, we're going to play the video and then we're going to have a discussion. So this is in line with some of our recent proposals that we spend a little more time on less formal presentations, which might take up most of the 2 hours we have at our disposal, and maybe spend a considerable amount of time in a more informal chat. Well, I'm delighted that John is actually here himself, so that will help us when we get to some of the feedback, perhaps some questions and discussion, which John will be more au fait with than some of us. But we're happy to take part in it. I don't see any yet comments from the Facebook and YouTube, but no doubt they'll come in presently. So now I don't see anybody like Franklin here at the moment to assist me. So you'll have to bear with me. I have the link to my video now. And I think the best thing maybe is to share it with you. Yeah, okay. So let me see. Let's see. Can I present? I share the video file. Let's see. Can we do that? Let's see now. Okay. Excuse me. The video file is embedded in a link. So I think I'd better share my screen and go to the link. I'll do that. So once again, thank you for your patience. Sure. Okay. Now let's see. Can we get this up now? Let me see now. Here we are.
outburst from the galaxy center. The galaxy means, this capital G here means
I'm just going to stop it for a second, and I'm just going to check, say with John. John, could you hear that? And it was playing all right.
Yes. Yes, I heard it.
Okay.
I think that's the right one. Cosmology.
Okay, well then I'll proceed. Thank you. I just wanted to double check that I didn't waste the next hour with nobody being able to hear it. So let me get back to it now. Right. Nice to be able to get back to it. Once I stopped it. So now where's it gone? Oh. Got it here. I may have to start it again because it seems to have disappeared for some odd reason. Okay, I'll start again. Sorry about this. I think we got the wrong one there. Okay, I have it now.
This video is a continuation of the Scalar Theory of Everything video. It is about the big, that is, about cosmology. The previous episode of the CNPS had the introduction to the Scalar Theory of Everything on 17 February. This is a link to that video. STOE is concerned with ontological reality and causality first, then math to describe reality and causality, and then only sufficient math to make predictions. Let's start this video with a little introduction about how I'm going to talk about the cosmology. And I'll do this by an example of how we can rephrase Newton's laws to show the difference between transformation and mapping concepts and measurement and calculation. So to start, you'll note that you measure distance between bodies and ticks of a process which is assumed to have a constant duration, a clock. You calculate acceleration as a first order effect. Then you map, which is a mathematical operation, the calculation to a fictitious, not ontologically real force called inertial force. To do this, you apply a constant of proportionality, here we're going to call it MI, called the inertial mass of the body. We can also postulate another fictitious force, here we call it Fg, called the gravitational force, which is how the body influences or causes changes in the plenum. And this is action by contact with a real plenum. The plenum change is propagated throughout the plenum. That's the nature of the plenum. It propagates waves. The gradient of the plenum acts by contact with the surface of Hodge. Remember, this differs for photons, where there's one surface direction along the perpendicular to x-axis. For neutrinos, there are two surface directions, and for baryons, there are three surface directions. Then suggest that the F's, our vectors, are proportional, that is, say, are related by a proportionality constant, which is called the big G, or Newton's gravitational constant, and the body characteristics, Mi and Mg, are assumed proportional, and they become part of the G, of course. Then note the plenum between them obeys the spherical principle. That is, big G includes three proportional constants, Mi, Mg, and a distance relation constant. The motion, which is what is observed, is obtained by inverse transforms. You'll note here we're talking about forces, not energy. So in general relativity, we take a measurement. This creates forces. The forces then over distance and time are energy and momentum. The space-time gradients, which is the mapping, change in energy, and these then produce changes in the world line of bodies by the inverse transform. Or in the STOE, we measure relative distances of bodies, which then gives you the plenum changes. These then cause forces or gradients in the plenum acting on bodies, and these by inverse transform causes changes in the motion. So the plenum is somewhat analogous to space-time. Physics has three general kinds of creation myths. The Big Bang, of course, where the universe had a beginning, then matter condensed into galaxies. The quasi-steady-state cosmology suggests the universe is eternal with expansion or with cycles of expansion and contraction. And then we have the STOE creation myth, which doesn't really say much about how the universe came to be. The universe may or may not be eternal, and it has cycles of temperature increase, which is expansion, and decrease, contraction. Now, the STOE philosophy here is that we have a sphere of things that we can measure and understand, and another sphere of somewhat we can predict. And outside of that sphere, we really can't say much, except by hand waving and very spiritual type arguments. The Big Bang suggests all particles have a world line, and that's what you do is you track the position over time with one time and place of creation. The quasi-steady-state cosmology has a world line of particles, but the particles are created in the universe over time. That is to say, the quasi-steady-state cosmology introduces a creation field, uppercase C, a scalar at center of all galaxies. That's going to be important in a bit. The STOE adds to the QSSC particles also have annihilation, that is to say, a termination of their world line at sinks in elliptical galaxies and sources in spiral galaxies. Sources and sinks in the STOE allow the universe model to be finite and bounded. Annihilation of particles out of our universe is not a new idea. Here's a paper in 1994 that suggested annihilation, but their annihilation of what they had to do to satisfy the equations they were using, general relativity field equations, still had problems. That is to say, the source and the sink had to be kind of close to each other, and the dust was in intergalactic space. But intergalactic space is relatively transparent. And this is why the STOE abandoned general relativity field equations. The reference for the QSSC is here. It's a different approach to cosmology. The QSSC also uses general relativity field equation. Here you see the normal right-hand side with the cosmological constant, this thing, on the left-hand side. On the right-hand side, we see the gravitational constant and, of course, the stress energy tensor. And here Narcalar adds the creation tensor, where the creation tensor is a scalar field which arises explicitly from mass world lines at the beginning of the particles, i.e. when there is creation of particles. Or in the STOE, we add annihilation in the STOE as part of the C. The left-hand side you see here is the mapping. And this then is not real. It's a mathematical mapping. Take note of where the cosmological constant is. In the QSSC formulation, the thing that stands for relatively dark energy, the cosmological constant, is on the unreal side. It's the mathematics. You'll see in some statements they'll put this thing on the right-hand side, meaning that they're suggesting that the dark energy is real. Here in the QSSC, this is the creation, so we don't need dark energy, except as the mapping. The left-hand side is the geometry of space. Note geometry, and this is what Riemann does. He takes and eliminates one constant on the right-hand side by making it geometry on the left-hand side. Is it a real component of the universe or a mapping? We're suggesting here that it's a mapping. If you consider it a real component, then it indicates the maximum speed allowed for light is c. And this conflicts with entanglement, Coulomb speed, and gravity speed, as noted in the first video. Therefore, the left-hand side is a mapping. It is not real. Before about 1990, the steady-state idea of oil considered the creation of particle world lines to be in intergalactic space. This idea was rejected. The last rejecting observation was the uniformity of the microwave background radiation. Then the creation site was changed to be at the center of galaxies, and this became the QSSC on the right-hand side of the field equation. You know, the dark energy term is on the left-hand side, as we noted before. In the QSSC, there are many creation events, and Narcalar has been writing papers over the last decade or so about these many creation events at the center of galaxies. These many creation events cause the creation of world line of particles, or Hodge, in the STOE. The STOE adds another constituent of the universe, the plenum. And so Hodge and plenum are both real. The plenum being real is one of the issues which the STOE has to deal with. This creation and subsequent nucleosynthesis, that is to say, combining the Hodge and plenum to form particles, causes the outflowing of bodies and plenum from spiral galaxy's center, and which resolve many observational issues of the Big Bang, including the need for the ad hoc additions of dark matter, dark energy, and inflation. The plenum idea comes from the QSSC, where Scalar's model had to include a negative energy component in the creation field stresses, which effectively is blowing space-time, the left-hand side, outward from the center of galaxies. That is, the plenum on the right-hand side is a real component of the universe, and its gradient is outward to create the QSS need for a negative energy. So, no infinite curvature nor black hole horizon on the right-hand side. STOE does not use the GR mapping equation. Three arguments that have been used against the steady state model. One is the greater number of radial source galaxies further, let us say billions of light years, than near the universe. That suggests that the universe has evolved, and this is based on redshift as being a Doppler effect, which we're going to argue with in a bit. QSOs have high redshift, which is taken to mean further away, again suggesting the universe has evolved. Redshift, again, is assumed to be a Doppler effect. And the third is that the CMB, or what they call a cosmic microwave background, is a black body radiation in all directions, assumed to be cosmic. It may not be cosmic. The steady state model has no explanation, but the STOE is going to come up with one. The next 5 slides are from this book by Binney and Merrifield, which is a fairly thick book, and it's fairly detailed in terms of observations. It's an observational book. Okay. We're going to look at what's the difference between elliptical and spiral galaxies, which Binney and Merrifield puts great emphasis on. The great majority of elliptical galaxies are observed to be much poorer in cool gas and hydrogen than spiral galaxies. And there's the page numbers. The bulk of the interstellar matter in spiral galaxies is molecular hydrogen. This is the 22-centimeter line observations. In elliptical galaxies, the bulk of the interstellar matter consists of hot plasma distributed approximately spherical rather than in a thin disk. A characteristic of elliptical galaxies not found in spiral galaxies is that the X-ray surface brightness is nearly proportional to the optical surface brightness. The study of dust lanes suggests the gas and dust are falling into elliptical galaxies and lenticular galaxies and are formed internally in spiral galaxies. That's to say, they're formed internally close to the center of the galaxy and are traveling outward. Some evidence has been presented that suggests irregular galaxies will settle down into being normal elliptical galaxies, and so too also with radial source galaxies. Low surface brightness spiral galaxies, the outer rotation curve generally rises, and we'll see that here in a bit. In contrast, ordinary elliptical galaxies with luminosities close to the characteristic luminosity, and this is an experimentalist number, show a nearly Keplerian decline with radius outside twice the galaxy's effective radius, enclosing half its projected light. The study of gust lanes suggests mass is ejected from spiral galaxies. Galaxies in clusters are much more likely to be elliptical. Spiral galaxies lie further from the center of clusters than do elliptical galaxies. So here then is a cluster structure, which I call a cell. You see spiral galaxies around the outside and elliptical galaxies in the middle. crudely, the diameter of these things is roughly 10 milliparsecs. In summary, the Big Bang suggests infalling, condensing matter into galaxies. Now, this fits elliptical galaxies, but spiral galaxies reject the Big Bang because they show things flowing out. The QSSC suggests outflowing matter from galaxies. This fits spiral galaxies very well. And many of the analysis that Scalar does in the book, he's talking about spiral galaxies anomalies in the standard model. However, elliptical galaxies reject the QSSC because they have stuff flowing in. The STOE suggests sources, matter flowing out, and sinks, matter flowing in, so the STOE suggests both. I started thinking about the STOE basic concept around 2000. I first applied it to cosmology and astronomy through till about 2009, and then started working on the other end of things, that is, say, the small, which we've already covered. Here we have the universal equation, which calculates the density at any given point. That's this value. It's dependent on sources, source strengths at the center of spiral galaxies, and the strength of the sink in elliptical galaxies. You'll notice that you take the source and then you subtract the mass that's around the source, that is to say, the spiral galaxy mass, and you then have the contribution to the density at rho at some point in space. And this is true throughout all the space. We take the source strengths, and the sink strengths are characterized by the blue band luminosity because that number is available for most galaxies. Now, there's a problem. The B-band luminosity is not all the energy that galaxies put out. So there's a problem which we will address here when we get around to talking about the data of B-band luminosity versus galaxy parameters. Also notice the relative contribution to the universe energy, the plenum density, is slightly different for source galaxies and sink galaxies. And so the universe has a net rho in because of that difference. And that's going to become important when we get around to looking at the cosmic microwave background. You'll note that each source and each sink has around it a lot of mass, which is the galaxy that we measure. And that mass has a contribution to the rho here. So a source galaxy is its source at the center minus its contribution from the mass. And of course, the gradient of the rho then produces the force on the rho, which gives you the motion in the rho. The STOE applies the spherical principle, which implies that space has three and only three spatial dimensions. The force that results from the gradient of the rho is the only force, and it's a magnetic force, as we covered in the first presentation. Therefore, the speed of the force determines the time characteristics in the universe, and this is process time. Let's talk about the big now. Now we're talking about galaxies and galaxy clusters. Before we talk about the relations of galaxies, I need to make some speculation about what black holes are, and that's what we're going to cover here. You'll note that this is speculation. Recall what photons and particles are. So here we have an electron structure, which is a structure of Hodge, and here we have a photon structure. you will note that there's a distance between the Hodge, and this distance is determined by the rho density in this area, which is determined by all matter, all sources, and all sinks in the universe. This then is a neutrino, and you'll see that you build up structures, as we covered in the first video. We build up structures by a T structure here, which you see here. This is a very strong structure. In the model here, you can take a structure like this and drop it, and it generally tends to stay together. Structures without this T are very weak, and they tend to fly apart fairly easily. Of course, if you do this T structure in a three-dimensional setting, you then end up with electrons and other baryonic particles. In a very high plenum density environment, the distance between the Hodge decreases, and therefore, if you had then a strong structure in a low rho, you now have a weak structure in a very high rho situation, such as you see here. In my opinion, it's my model. The STOE avoids singularities and infinities by means of requiring the surface force on the surface of a Hodge. And then you have contact both in causing the rho and in the rho gradient on the Hodge. There are no singularities and therefore no infinities. Because distance has meaning as only the distance from a Hodge surface, we have different types of distances between Hodge that are in a particle and between particles because of the Hodge in the particles. And they're dependent on the plenum density. Now, the support for this structure comes from a couple of different areas. One is, as we talked about, the Michelson-Morley experiment. Perhaps Fitzgerald was correct. That is to say, because we see that along the sun-moon axis the rho density changes, so too then must the length of photons and the size of electrons change with that. Therefore, the apparatus condenses and expands depending on the rho, which then is what is being measured. So Fitzgerald suggested this, and that turned into the Lorentz equations, and that is correct for length, but not necessarily for time, that other stuff. As long as the number of Hodge stay the same in a structure, the mass stays the same also. The second support for what we're going to talk about here comes from gamma ray outbursts from the galaxy center. The galaxy means this capital G here means that this is the Milky Way galaxy we're talking about. And it has been observed that there are periodic gamma ray out. You generally find that they emit radiation pretty much across the spectrum. These gamma ray bursts from the center of our galaxy are without accompanying other radiation. And what the STOE is going to suggest is that is because the very high rho, very high plenum density, next to the source is going to be very high, and that very high is going to compress and therefore loosen the structure of black holes. It's going to essentially cause the black holes to disintegrate, and out comes all these very high gamma ray bursts, gamma rays being photons from the center of the galaxy. So here we have a galaxy cluster. You'll see here that we have spiral galaxies over here, elliptical galaxies here in the center, and spiral galaxies are a source of radiation which is then leaving. Now, just outside the source, and typically this is within now, the measurement is 12 AU. We have a bunch of black holes inside, say, 12 AU. This is determined by the S stars more recently. And out from that, you then have hydrogen, because by the time you get to 12 AU, nucleosynthesis has happened with the Hodge and Roe, and you now got particles, even hydrogen atoms. And this is verified by shock hydrogen gas clouds that seem to be exiting the area around the spiral galaxy center very rapidly. Of course, between sources and sinks, you've got light and Hodge, but not all hydrogen leaves. Some of it comes back in, forms denser particles through suns. These suns then turn hydrogen into other atoms, molecules, and eventually they become dense enough so that they have a supernova. A nova explosion does a couple things. One is a lot of the matter that's on the outside of the iron core of suns is ejected as particles, which are heavy elements, and these go over to the elliptical galaxies. Now, these heavy elements, rocks, are falling into elliptical galaxies, and they've traveled some distance, and they're under a force all the way, and therefore they come in very hot, very fast into elliptical galaxies. So they're the sinks. They come in so fast that some of them get ejected out again, and this is called a cooling flow, where they're ejected out a little ways, and they cool down, they slow down, and then they fall back into the elliptical galaxies. And eventually the matter and the plenum is annihilated in the sink. The other result of a nova explosion, ultimately is black hole. There are apparently thousands of these black holes, sun-sized black holes, around the center of our galaxy, but outside that 12 AU radius we talked about. And these fall into the center near the source, where they are evaporated out, and we start the cycle all over again. The first two of the three arguments against QSSC model, which we talked about before, depend on galaxy redshifts being a Doppler effect. So the first data examination that we want to undergo is to suggest another model for galaxy redshift being due to another effect, which can be related to other data sets, such as the Pioneer anomaly, which also in the STOE model is viewed as a frequency shift. First, we have to determine the Ks that we talked about. So we take a look at close to us, and as we go out in the spherical shell, we measure the B-band luminosity ratio for sources and sink galaxies with the distance. And what you see is that as you go away from us, the ratio declines. I mean, we're actually close to a source galaxy, so you'd expect that to be very high. But as we get into the center of our galaxy and we start looking to include other galaxies, you see the ratio declines and becomes relatively steady. Where it becomes steady is at about 2.718. That's the ratio then. And this is found in this paper. So we substitute that in the universal equation, and here it is. For each one value of whatever, we have 2.718 impact of spiral galaxies. And here we've substituted the gravitational constant for the effect of mass. you note that the Putnam density has to be greater than 0 everywhere in our universe. The net rho for a galaxy, as we talked about before, is due to the source strength minus the gravitational mass contributions. This is galaxy redshift, and this data is using Cepheid variable distances. It's called the Key Project data, which is a virtual standard these days of what generated the Hubble constant here. And this is the line that it generated. You will notice we're looking at the redshift as it's measured versus as it's calculated by the equation. The data from here on out to about in there, about 10 megaparsecs away, is in our galaxy cluster. And it's very good. This data corresponds to the tip of the red giant branch, which is about the limit you can do with that kind of a measure, and with parallax type measurements. And the data here is pretty good. However, out here, it isn't so good. This data comes from other clusters, Virgo and Hercules predominantly. Overall, the correlation coefficient is 0.8, which is poor. But this Hubble constant is key in modern cosmology. It's based on very poor relation overall. Now I'm using correlation coefficient. The type of statistical analysis that you do has a lot to do with how you accept data like this. Personally, I would not. I mean, look at these things. They're really way out. And of course, you've got something off. The ones that are in our galaxy cluster, such as Andromeda, have actually a blue shift. So this, to me, signals problem. But this is fundamental to the understanding of cosmology. And you remember what redshift had to do with the problems that standard cosmology says with the QSSC. Recall from the first presentation that light or photons is a column of Hodge. The energy in the spectrum of photons depend on the number of Hodge in a photon. The plenum density, rho, between galaxies is low, which makes photons very long. The ends of photons are subject to spallation. This is the STOE model of friction, which is where end Hodge simply are removed from a photon or other particles, which changes the energy or the redshift. The derived equation in the STOE model is this. There are 5 constants, these K's, and these are calculated, the P and all are what's happening to the rho as the light comes from the galaxy to us. There are 5 constants and 32 galaxy data points, so you should be having pretty good data here to calculate. This is a sample of the calculation where we look at the rho at each point from the galaxy to us, and what the rho calculation of all the other sources, sinks, and matter does to the rho. This line and going here is a 1/r line, and that's what gives you the Hubble relationship. But you'll notice that there are deviations here and here and a little bit here in the straight Hubble relation for this particular galaxy. Here's another sample calculation for a different galaxy. You can see that one. And here you've got a deviation from 1/r. Here you've got some real deviations here. So this one is going to show a lot of difference from the Hubble all these things, and what you end up with, the data as taken, ends up with a correlation of 0.88. Still not very good, but still much better than accepted cosmology. And you will notice that we do have a few outliers, where their error curves do not intersect on the line. One of the things I know about these outliers is that they all have a QSO close to their line of sight. Here's Haltonarp's Seeing Red book that he wrote. And if you take the QSOs exactly as Haltonarp says they are in his book, that is to say they are much closer to us than the regular Z value would indicate, and that they are emitted from source galaxies. That is to say, we take the distance to be the source galaxy redshift rather than the QSO redshift, and we end up with a correlation coefficient of 0.93. Much better. I started to look at the same thing with elliptical galaxies, meaning radio source galaxies, and there you get into a lot of difficulties because you can't come up with a good distance measure for those things. This is from Haltonarp's book. Here we're wanting to kind of justify what we say about these QSOs. This is the book has many photographs like this where he's looking at a spiral galaxy here, and this then is a QSO, and he's seeing that, which you see, he says is a dust lane from QSO to the spiral galaxy, which means that this thing, independent of what the redshift says it is really actually very close to this, which has a much lower redshift. This is another graph that he had where he's looking at a spiral galaxy with a redshift of 0.008 here, and then he's looking at what he calls other QSO galaxies. Here you see 2.3 going to 1.97, and here is a QSO near another galaxy, or at least close line of sight. And you'll notice, like Haltonarp does, is that the redshift of these QSOs starts high, 0.81, and declines as it goes away from the center galaxy. It's another one of Hart's, the origin of QSOs, and strictly speaking, the origin of spiral galaxies. You see what's being suggested here is that the spiral galaxy is a source, and it's emitting not only matter that stays around it, but it's emitting another source, which eventually in time is going to have matter around it. And the reason why the decrease in the Z is because of that negative matter factor. A QSO then has very little matter around it, and therefore it has a high redshift of the source only without the matter. I mean, that's the model we're presenting here. That's the model that Haltonarp presented. Well, this is the data. However, if we take the X factor from the previous equation and plot it, there's their X factor, and there's for the 32 galaxies, which have a distance calculated by Cepheid variables, not by redshift. And we end up with a line. This line looks a lot better overall than what the Key project had, but yet this is still the Key project data. And the correlation coefficient here is 0.93, which is quite good. But the Hubble law here then becomes, with a shift to 110, and plus or minus 20. But this factor here in that distance allows for these, which are blue shifted galaxies. Holmar suggested what he called intrinsic redshift. He suggested particle masses change on cosmic timescales. Thus, they emit a redshifted light the further you go back in history. You see what he's getting at here. It's very difficult in cosmology to consider this because one of the basic assumptions in doing cosmology is that matter in space is like here on Earth. Therefore, we can take emitted radiation from things far away to be just like it is here on Earth, the spectrum being the same, hence redshift. So, but, you know, I don't like this intrinsic redshift myself, but that's just a report. That's what he reported. The STOE suggests the QSOs are young, just like Hart and Lobb did. The model is that sources emit mass and some of it stays around the source, thus forming eventually a spiral galaxy. That mass then, as it forms, reduces the redshift that it measures. Thus, this redshift effect is the net of true source strength minus the mass effect. Mature spiral galaxies then reach a temporary balance to emit an amount of B-band luminosity light. This stays relatively same because some of that matter that's emitting the light is going into the center of galaxies, being broken apart, the black holes being broken apart and being re-emitted out. So the QSO's age is developing more matter, that is, say, lowering the redshift as they develop. This is another observation. It's a plot of redshift, C, versus the number of galaxies with that redshift. And you'll notice it's what's called a periodic redshift here, here, here. And there are some gaps. This is a problem for standard cosmology. Why should they exist like this? Why should there be these periodic redshift amounts? Here I look at the redshift and distance versus angle from, remember what I said, the center of cells. Here is a look in the direction of this galaxy, which is in a cluster of cell, and we're looking at the measured Z and the distance versus angle, as we view it, angle from the diamonds, which are elliptical galaxies. And you see in the center of the galaxy, here and here, the distance as measured by various things appears, well, uniform both sides of the center. In looking at Z, you see that's not true. It appears as though everything is all bunched up at a given distance. Now, the problem we have is that when you look at that same galaxy is the center of a cluster, and here you see the cluster looks fairly uniform here against our background. So there should not be a grouping of Z or distance, spherical or near spherical, in our view this way. Why is it different along our line of sight? Well, that's because the Z, the redshift, is being influenced differently by elliptical galaxies and spiral galaxies as the light passes by them. The third observational argument against the QSSC had to do with what is called the cosmic microwave background. Now, the STOE is going to suggest that it is not cosmic in the sense that it's due to some very, very far distant radiation, but it's due to the negative feedback flow of the components of the universe, that is to say the Hodge. You remember that we had sources emitting stuff, but some of which goes to the elliptical galaxies, all eventually does, but some of it comes back in through black holes, which is re-emitted back out, and eventually everything flows to elliptical galaxies. That is to say, the microwave background that we're measuring is really measuring the temperature around galaxy clusters. So here's how we're going to calculate it. We have a temperature from all time. This is the total amount of sources and their source strengths minus elliptical galaxies and their source strengths over time. So it's Q in, energy in, minus energy out in the universe. And that is limited to energy in versus energy out of a cluster. We apply the negative feedback principle. That is to say, we imbue the elliptical galaxies with a feedback mechanism. The fine-tuned parameters are controlled by a negative feedback loop. So, you have in your home, we hope, a thermostat which controls the temperature. Temperature goes too high, air conditioner turns on, lowers it. Same thing here. Mass in a sink galaxy becomes too high. The sink becomes too powerful. It drains more energy, more matter and plenum out of the universe than the sources are providing, or vice versa. Sources increase the heat energy in the universe. Sinks decrease the heat in proportional to the mass of the elliptical galaxy. This is now simple math, apply the heat equation. This is done in lots of books. And what you end up with something like this. You'll note that in our equation, we determined that the average temperature, that's to say the factor in front of the spiral galaxy, factor was 2.718. That is the hunted temperature, meaning at the thermostat setting. Looking at Penrose and his papers, he's saying that the temperature going down means that the sources have been emitting more, but the elliptical galaxies are sinking more and more and increasing their sink strength. Therefore, the temperature is coming down here. That's the Penrose kind of thing. But you'll note that some time ago, according to this model, the universe turned around and started increasing temperature. That is to say, the sink strengths were low and the source strengths were high, and therefore the temperature coming into the universe was increasing. Increasing temperature means universe expansion. I wonder if in a few years that the James Webb Space Telescope isn't actually looking out into this zone. And why do those galaxies out there look so mature? Well, because they are mature. And they're more than 14 billion years ago when the temperature was decreasing. The communication in standard Big Bang cosmology requires the radiation from one end of the universe be felt at the other end of the universe. This creates then what's called the horizon problem. In the STOE, the horizon problem is solved. That is to say, the radiation that need be effective only be across a cluster, not across the universe. And therefore, the microwave background is being adjusted in temperature, due to a cluster, not due to the entire universe. In conclusion, the STOE explains many cosmological problems, including the Machian model, and it has only 3 spatial dimensions. STOE cosmology and the quantum scale model support each other.
Right. Let's see if we can. Get rid of that. All right, just stop sharing my screen now. Stop screen.
So now,
Okay.
now let's address the B-band luminosity issue
one?
that I talked about before.
Hold on, there's something else
Here
there.
is a sample of the data. This one in particular is looking at the asymmetry of rotation curve.
Get rid of all those. Get rid of that. See now. Stop sharing. Let's see. Can I? Well, I want to see now. Have we come back? So I'll try John again. John, have I stopped sharing my screen? Yes.
What I
hope
see
so.
now is you and me.
Okay, but that's bad because I want you to see your own screen. So let me just see now. Right, and let me see now. How do I stop sharing? Stop sharing. I think I'm going to have to leave the studio just momentarily and come in again. So if you just bear with me for maybe a minute or so. So I hope we're back now to the normal situation. Now, there are a number of people in the green room. Let's have a quick look at whether some of these comments, because I must confess I haven't been looking at the comments at all. My eyes have been glued to the video, as all of yours have been, I'm sure. So the best thing I can do maybe is bring John up with regard to the questions, and then when we have the discussions, we'll bring everybody else up. So Quest has a question here: are all physical phenomena considered Hodge? see, you said, I think, that the Hodge and the Feynman sort of make up, um, all matter.
The two fundamental components of the universe are Hodge and plenum. Bodies, matter, is Hodge and plenum combined.
So you need the two things. I hope that answers Quest's points there. You can come back
That is usually in the STOE the problem. It's a different kind of concept than you're normally used to. But with these two components, you also get only one universal force, not the four of the gut, and you get a universal equation which no other cosmology model has.
Robert K says all galaxies are attracting each other. A spiral galaxy could be when a galaxy with more mass near a galaxy could create the outward flow.
Well, the STOE disputes the first statement there. If you'll notice when we're talking about Harp's observations, those galaxies are flying apart. And those QSOs in the STOE become spiral galaxies. So mass in a galaxy, all the bodies of a galaxy are repelled by the source at the center of spiral galaxies. So essentially, the masses of the spiral galaxies are repelled from each other. It's not,
okay,
and of course.
Okay. Okay. We'll have a fuller discussion presently, gentlemen, but let's just try to capture some of these main points first. He says, Quest, why don't galaxies collide or even combine?
Well, that's because galaxies form around sources and sinks. Now, what a source is a very high rho, very high plenum density, and that repels matter. So what we observe is, of course, matter. We don't observe the sources, we observe matter. And so this very high plenum density around a source repels matter. And that's what causes the rotation curves to be up, not dark matter. It's that extra force of repulsion.
Actually, I can see that thankfully you have been answering some of these questions on the chat. Thank you. Okay. He says the chat room is frozen. Well, I don't know. We'll see it at that moment. Yes, some other points you've been answering about the relative radius of the electron and the proton.
Well, that was covered in the first video.
Right. I don't know. Roger Anderson says, Hodge is supposed to be the most fundamental particle, presumably, but point particle is the most fundamental. I don't know if you have any comment on that, John.
Well, this is kind of a subtle thing. The idea of a point particle is a mathematical concept. It's not a physical concept. Okay. But this leads to a problem, which I consider to still be a problem with the STOE, as well as in all other theories. Point particles exist because there's always something in the math that says you go a certain distance and suddenly the source of whatever it is you're causing a force seems to be from one point, such as when you look at the Earth, oh yeah, I did answer it there like that.
Yeah.
But the problem is whether or not the plenum obeys a heat equation or a wave equation. A wave equation means you have the waves, but a heat equation does not produce, it doesn't produce waves directly, but it does have a point kind of situation. And a point particle then is when the spherical principle, this is the Newtonian spherical principle, applies.
I didn't myself see how you accepted the concept of length contraction, but Quest says so the STOE does. Is that true or false?
That's true. The STOE accepts length contraction, but not the rest of special relativity, not the constant speed of light, not time dilation.
Okay. Well, maybe we'll discuss that a little more.
And that is kind of a little bit of a mystery. The STOE accepts length contraction in the sense of Fitzgerald, meaning, and Fitzgerald and Lorentz, by the way. He followed that up, saying particles go from spherical to being kind of oblong as they travel, which means you have a physical length contraction. Well, the STOE accepts that. Except that here what a particle is combinations of Hodge, and as you increase the density, okay, you change the distance between the Hodge in a particle, which changes the length of the particle. See, here I got 4 fingers, and they have that length. Now change the density. The particles become like that. You see the length contracts. So in the Michelson-Morley experiment, you'll note that they did detect a change. I mean, that's the modern generally thought that they didn't detect any change, that it was a null experiment. They certainly did not detect the ether, the luminiferous ether. But they did detect the change. But that change was along the Sun-Earth axis, you see. And that's a plenum change. It's just the kind of thing, well, you call it a gravity change, and you then have Earth tides.
Yeah, Harry, I do see you waving, and I'll bring you in very shortly. If you just give us another few minutes just to get through most of these questions, because I want to get a few of you to talk in detail. So let's see, can we briefly get through these questions first? Yeah. So you don't accept this Doppler shift, questions. So the redshift doesn't suggest distant objects running away.
Well, that's the STOE model is not a Big Bang model. And one of the differences here is just exactly what is redshift. Now, in the Big Bang model and accepted physics today, they say redshift is due to a Doppler shift. And many people even just call it a Doppler shift and not a galaxy redshift. But it's not a Doppler shift. What it is a tired light model, as some others have suggested.
Okay, well, some of these things seem to be at variance with some of the ideas that I've been looking at, but we agree on that certainly. My analysis would be a tired light position as well, allied with or allied to sort of an ether entrainment, because I'm wondering what your concept. Do you conceive of the the plenum as being what others might call an ether.
Well, yeah, I use the term plenum rather than an ether because there are many concepts of what is an ether. Luminescence ether is one of them, which is, of course, rejected by Michelson Morley. But many people consider an ether to be particles, be made up of particles. And even in the questions we saw here today, we saw some indication that people are considering an ether as being composed of particles. Well, no, it's not. It's a continuous substance. It's in relativity, it could be the left-hand side of the equation, the space-time thing, you see, or a quantum vacuum was another description of it. But it's a continuous, ubiquitous component of the universe, and it's fundamental, which means that's it. It's not made of anything.
Okay.
And of course, the problem with that is, does it exist? The age-old existence problem. And the STOE maintains that the plenum does exist as a component thing in our universe.
Okay, I mean, question says many ethers don't think the ether is composed of particles, though. Well,
that's true too.
Okay. Well, we can come back to some of these points because they're more in the nature of discussion. Harry has been asking for a few minutes to come in, and I'm going to add you to the stage, Harry. You're welcome. So, would you like to put some questions or some points to John?
Okay, you kind of lost me in places, all right? And, okay, so let's go back to what QSSC is. I kind of missed that. What is QSSC, or did I say it wrong?
Quasi-steady state cosmology.
Okay, so that's Hoyle and Narliker. That's this book here, correct?
I can't
Action
read
at a Distance in Physics and Cosmology by Narliker and Hoyle. You familiar with this book?
Yes, the sort of thing that Hoyle was certainly looking at.
Well, Hoyle basically invented the.
I don't know. Can you see that?
Fred Hoyle, yeah.
Okay, I'm not familiar with that book, but you're talking about the Hoyle's cosmology, basically. Okay, can we get this straight? You're talking about Hoyle's cosmology. Hoyle invented the steady state cosmology. Then that was Hoyle and Gold, if I'm not mistaken. Then he got together with Narliker, okay, and came up with this book here, and then he published a number of other books, which I have, that basically explain this theory in more simple form. So, but that's the theory that you're talking about. Is that correct?
Not the steady state model. Hoyle and Gold, I guess.
It's not really necessarily the steady state. It's a kind of.
Yeah.
You're not familiar with this book, and you're not familiar with his theory. Okay. All right.
Well, I'm familiar with the steady state theory. I'm not familiar with that book, but I am familiar with the steady state theory.
Well, this is the foundation of the QSSC theory, as I understand it.
Well, am I correct in thinking then that the original steady state theory... I'm
trying to understand what he means when he writes down QSSC.
Yeah, okay. Well, let's try to clarify that a second for people. Is it correct to say that Hoyle's original idea of the steady state theory was modified by introducing things like continuous creation to try to accord with mainstream ideas that, to a certain extent, Hoyle accepted, although he didn't accept, the Big Bang? Would that be a fair analysis? Because there was an evolution.
Well, Hoyle invented the steady state theory with Gold. Hoyle invented the steady state theory with gold, and it was before the Big Bang theory. Okay. And there were other theories. There was Lemaitre's theory, and then there was the Friedman universes and all, okay. But the Big Bang didn't really come into existence into the microwave background radiation. And then everybody said, oh, yay, that proves the Big Bang theory. Okay. And they'd already sort of dispensed with Hoyle's original theory. So Hoyle then modified his theory, and I think it's gone through several modifications. That's the point that I'm trying to get at. But it's basically Hoyle's theory fundamentally modified over the years. Is that correct? That's what I'm trying to ascertain from John.
You're being too general, and you're missing something.
No, I'm just asking you the question. What is the origin of this QSSC theory?
Yeah. Okay, let John get back there. Harry, let John get back there.
When the steady state theory of Hoyle and gold, and it's evolving through the 1980s, was rejected in the early 1990s, they modified it to come up. Narklar and Hoyle modified it to come up with this QSSC. Now, the modification was to change where matter was created. You see, the steady state theory had matter being created.
So basically, you're saying that I'm correct. Okay. All right.
So basically, you're saying I'm correct.
Okay. So we've established that. So we've established that the QSSC is the Hoyle-Narlikar steady state theory modified over time with changes.
As long as you include Narlikar. As long as you include Narlikar. As long as you include Narlikar.
Well, Hoyle died and Narlikar is still going on. He's a co-author of this book, which you apparently are unaware of. Action at a Distance in Physics and Cosmology. Okay, now on to the cosmic microwave background radiation. My understanding is that Gamow originally proposed that there would be that the universe has a temperature, and he calculated this temperature, and it was he sort of calculated the temperature based on some guesses that he made. Are you familiar with Gamow's calculation of the temperature of the universe?
I reviewed it years and years ago, maybe 2 decades ago.
Well, anyway, what happened was that they basically...
He didn't really calculate it. He guessed about he had a few assumptions. And this is other people back 2 decades ago, 3 decades ago. Other people had been looking at this temperature thing, the microwave background temperature. You know, it looks like a black body radiation, and that raises all kinds of red flags. It means it should do something. But people tried to figure out how to calculate it. And to my knowledge, the only one that's calculating a theoretical value close to what the microwave background radiation temperature is measured is the STOE model. All the others, when they first calculated it, before they actually had a measure, started talking about 5,000 degrees Kelvin, 5,000 Kelvin, 1,000 Kelvin, and that number kept coming down until it kind of got close to what they measured. But they still did not theoretically calculate what the temperature was measured at. The STOE is the only model that does that.
And how are you doing the calculation?
Because in the STOE model,
it wasn't really clear to me. It seems to me you've got some assumptions that I didn't really understand.
Well, the assumptions are fundamental in the STOE, that there are sources and there are sinks, and they act like temperature sources and sinks. And then you simply apply regular thermostat type temperature calculations. You have a thermostat, which is the amount of mass in the elliptical galaxies, and that controls what the temperature is. So you have sources putting heat into the universe, and you have sinks taking heat out of the universe, just like a thermostat and heater in a room.
Well, how do you arrive at 2.7 K?
Well, yeah. What the universe is, and this is going into something that I've kind of dropped over the years. What the universe is one heat step, and what applies then is the Euler factor. From source to sink is one Euler factor. You see, and that's
Euler factor.
Well, my understanding
is
my understanding is that
718 K. Okay, I'm
my
sorry.
Understanding. Well, as I understand it, Vladimir has proposed alternative in which he does a calculation of the CMB, and I'm not sure. Is he here? Ian?
He is here. Yes, we'll bring him in shortly.
All right, maybe he can. Anyway, my point is, I wouldn't. That he has an alternative viewpoint than what John's saying. Okay. Anyway. All right. I don't have any more questions right at this moment. What I'd like to suggest is that we have maybe Vladimir and John can get together, and myself and anybody else is interested, and we can talk about this cosmology stuff, because a lot of what you're saying, John, you're using Arp's work, which is very familiar to me and very well known, and Vladimir doesn't really know much about ARP at all. So I think that's where you can talk to each other and maybe exchange ideas.
Well, thanks for that suggestion, Harry. I'll bring it down for the moment and come back if necessary. But what I might do, with your permission, all your permissions, is bring Vladimir up the moment, just perhaps briefly to have a discussion on some of those issues, and maybe how the world universe model relates or doesn't relate to the work that John has done, the STOE model, maybe where they agree, perhaps where they disagree, where they take different approaches.
Thank you so much for the invitation. Thank you very much for your interesting talk about your model. Of course, there is no correlation between them. It's principally different models. That's why it's difficult to compare one to another. This is the first point. That's why let's see the key points of your model. Here he started already to ask you the questions about microwave background radiation. Let's start with the small issues. By definition, any black body radiation, and it's measured experimentally with accuracy up to 4 points after the point, digits after the point, it must be some thermo equilibrium between radiation and some matter. There is no other way to explain black body radiation, because photons, they don't exchange energy between each other. They can only have some bodies inside of them, outside, it doesn't matter. And there is an interaction between photons and some body in some kind of equilibrium. What kind of matter you have to provide black body radiation of microwave background radiation? What kind of body? Because it's against even the physical law. Physical law means body, photons at the same time in thermo equilibrium. Please answer this very important question, physical question, because there is no other way. because Big Bang model, oh, there is a change in the wavelengths. There is no explanation. What the wavelengths, how it's changed, what is the mechanism? I'm asking you direct question. You have black body radiation calculated by myself with accuracy up to the 4 digits. And what is the body? What is the body for this radiation? Because the sink or you generate some heat, you don't generate heat, it doesn't matter. What does matter? Body for providing thermal equilibrium for these photons.
So, John,
Well,
maybe the process.
What is the process?
first,
Because without body, it's impossible. It's against physics. I'm sorry.
okay, that's the second thing I disagree with then. First, saying anything is the only way that you can do it is a totally model dependent kind of statement. Within your model, that may be true, not within mine. The other thing is saying something is impossible when there's clear data that says it's not. I mean, this is stuff. Okay, now my model. Okay, let's get away from sources and sinks in the galaxy concept. Let's talk about what happens with a hunting of a temperature of a thermostat in a room. You have a heater, source of heat, heats the room up. When the temperature gets above some level on the thermostat, which you set, the heat turns off and the temperature starts dropping. When the heat gets below some level, which is set by the temperature of the thermostat, the heat turns back on and it goes back up. That's a fine tune. I mean, fine tuning is a thing in cosmology. People talk about whether things are fine tuned or not, but fine tuning is a thing is a process in the STOE. Sources put stuff into the universe, plenum and Hodge. Sinks take them out. Plenums and Hodge are energy, and you can convert that to energy, and sinks take energy out. And the thing that determines the rate at which energy is taken out is the mass in an elliptical galaxy. See? Now, it takes time to have the source put a piece of matter into the galaxy, into the spiral galaxy. Some of that matter goes out, and some of it comes back in, only to be ejected back out again. I think your model also had matter being ejected from source galaxies. I don't know, I think that. But matter is ejected from source galaxies. It travels to the elliptical galaxies, and there you have cooling flows. That's an observed phenomena, is a cooling flow of matter that is again rejected for a little bit out of elliptical galaxies to flow back in. But in the end, there's a net inflow of matter, which is the Big Bang kind of thing. And on the source side, on the spiral galaxy side, there's a net outflow. And that is the thing. And in the end, you're trying to find the hunted temperature. The hunted temperature is the Euler factor, right? And so you have the temperature of these clusters, these cells, increasing and decreasing, hunting the Euler factor temperature. So the temperature is increasing, which causes universe expansion, or more recently, temperature is decreasing, which is going down from 2.72 something or other down to the Euler temperature.
Gentlemen,
I'm very sorry. Let me continue to talk about this one and then some principal points. You're talking about temperature. Temperature is the average kinetic energy of some particles. You have energy of your plenum, and there is no articles in plenum. When you are talking about temperature, what do you mean? Because temperature of what?
This is measured temperature, and all measurements are of Hodge.
I'm sorry. One more time, the same question. Temperature of what you're talking about? Because there is a plenum, it's something, I don't know, perfect liquid or something, no particles at all. And you're talking about temperature of what?
Of Hodge.
It's a principal point right now we're talking about.
And I hesitate to incur the ire of either or both of you, actually. But you might forgive me if I say this is actually a very interesting conversation, whether temperature of Hodge or some other aspect. But I think I'm going to have to ask you, gentlemen, to follow Harry's suggestion, indeed, and follow through these discussions privately. We can come back to them.
One more question. Only
just one, because we want to bring some other people in, Vladimir.
Okay,
only
but
a few
one more
left.
question for the future discussion, because we are talking about elliptical galaxies, spiral galaxies, and so on. Where they came from, how they were generated, how they were originated. That's it, simple like this.
Okay,
because
so
if you have some evidence of your model, you must tell to us how they race, how they evolved, how they generated, all this process. Thank you so much for your patience. It's a very good proposal of Harry to talk about all these issues and some special discussions. You're absolutely right, Ian, as usual.
Well, thank you very much, Vladimir, for your understanding. And thank you for your questions. And actually, Jim has said it's very productive to have you two experts debate the issues. Would you like to say something very briefly to Vladimir's last point before we bring somebody else up, John?
His last point was about the creation?
About creation of spiral and elliptical galaxies, how they created.
The different types, presumably, yeah.
In different times.
The spiral galaxies are created by the sources. The source ejects plenum and Hodge. Remember that one slide where I showed you the source galaxies, elliptical galaxies? Spiral galaxies come from being around the source. It ejects matter, Hodge and plenum. It goes out. Some of it goes back in, meaning it becomes hydrogen. Around the center of the galaxy, that's shocked hydrogen. So hydrogen is being ejected from spiral galaxies. Some of it goes back in, and that then creates the spiral galaxies. You may remember the slide from ARP where it shows the high redshift of QSOs. Well, QSOs are baby spiral galaxies. And as these things form, they form matter, and there's more and more matter, and that reduces the redshift, and as they go out from another spiral galaxies. Elliptical galaxies are formed because this matter that's leaving the spiral galaxies eventually comes together and condenses, being forced into the center of a cell by the surrounding spiral galaxies. And so elliptical galaxies are formed from all this stuff that has been created, condensing, infall, just as the Big Bang model suggests.
Okay. Well, thank you very much. I might just briefly mention my own idiosyncrasy with regard to this, because I think I did mention it briefly during Vladimir's sessions. My own models would discount the apparent variation between elliptical and spiral and other types of galaxies. I say they're probably all essentially globular. And we're just viewing very distant objects, not as one snapshot, but at different points of their evolution. Because any point that we actually see at any given time must be the same number of light years away from us for us to receive the light now. If it's further away, well, the light hasn't been received by us yet. If it's nearer, it's gone past us. So I say they're sort of images, composite images. Anyway, that's something we could discuss it in more detail. But it's so. If you'll forgive me, I might ask Jim to come up now because he's posted a number of things here, and I'd like him to. So thank you very much, Vladimir. For the present, I'll bring you
Okay,
down.
okay. I'm ready to continue this very interesting discussion.
Yeah, and I think we've started something. We've started something either to be continued during today or the next two sessions, or indeed, in a more comprehensive way through private chat. I don't want that to be lost in any way. But James Keane, Jim, would you like to express the point you put down?
I have several points, John. Thank you for your presentation. Sorry, I did miss the first part via oversleeping. At any rate, one question is if light velocity c depends on energy density in the media through which it travels, in other words, a reduced density with reduced density media being traversed, could changes in density account for redshift?
Well, yes, but not directly. You're kind of implying that the change in density directly influences the size of a photon. A photon is a column of Hodge in the STOE model. The energy of a photon is the number of Hodge, and the length of that photon can change without changing the energy. And that's what would happen with a lower density directly, meaning the length of a photon changes, but that's not changing the energy, that is to say. But what happens in the STOE redshift model is that sources and sinks, as the light travels by these things, create different increasing and decreasing rho levels. And it's that increasing and decreasing which then causes a friction, which is to say it causes Hodge to be spalled off a photon. Am I following? Am I getting to you?
Well, I sort of yes and no, because actually I'll have to go to your website to become a little more versed in your work. I'm really very impressed with the work you presented previously on the double slit experiment, and I think that's amazing results you have there. A second question, and I'll close for now, is what data would support or exclude womb versus STOE theories?
Yeah, good question. What would, if we could arrive at it, not necessarily what has?
I missed the question.
Well, if you're, it's a fair question, John. If you're familiar with Vladimir's presentations on womb recently, in recent months, what data would tend to support one of the two approaches, womb versus STOE, compared to the other, or exclude one of the two? In other words, how do we proceed to design experiments or seek data to help us decide between these two models? If that question is posed clearly enough.
Yeah.
It's not a fair question if you're not familiar with womb.
That's totally a fair question. The next presentation that I have, that Ian has, the second one, is a bunch of experiments or observational data having to do with galaxies, such as rotation curves and the like. Now, if I remember the womb model, he has a fourth dimensional object that is putting into our universe matter and stuff. And the things that rejected the steady state model, right? Remember, the steady state model is that matter and stuff is created intergalactically. Well, that's very close to what the room, if I understood the room right, says, is that you have this fourth dimension and it's putting stuff into this universe. It's a little unclear to me whether it's coming in like a Big Bang at some point or whether it's generally coming in, which means between galaxies. Well, matter creation between galaxies has essentially been rejected by data in the 1990s. That's why the steady state was rejected, if you follow what I'm saying here. So, but if Room was to modify his theory such that he had his matter coming in through the sources in the center of spiral galaxies, then you would have the STOE, but then you have elliptical galaxies. You see, now in the Room model, you have all the matter and stuff coming into the universe. Well, and that means it's coming in someplace. And how do you explain then the other things, which I think Vladimir did mention, that in spiral galaxies he notes that the stuff in the universe in the spiral galaxies, such as hydrogen, tends to be flowing out from spiral galaxies. But now where I missed his understanding of what then is the difference between a spiral and elliptical galaxies, where matter seems to be inflowing into elliptical galaxies. I mean, if his galaxies are outflowing, he's talking about spiral galaxies. If matter is inflowing, then you have elliptical galaxies. And I think he used this term galaxy. He wasn't specific between these two. But that may be my misunderstanding.
Well, perhaps, Jim, if that's all for the moment, I might just try to get Vladimir in just for a brief moment just to address that point.
Yeah.
Is that all right, Jim?
Thank you, John.
Yeah, thank you very much, Jim. Vladimir, could I impose upon you very, very briefly, we're running out of time now, and I'd like to bring Denny in as well, to address that point. Does the womb model conceive of this inflow and outflow of material as distinguishing between the two types of galaxy, the spiral and the elliptical?
My proposal, please don't cite my model, because you're absolutely wrong. There is no correlation with Big Bang with anybody else. That's why let's start discussion, and let's start from the very beginning. In my point, instead of creation matter from one infinity energy density point, as it is in Big Bang, totally wrong. In my model, matter, universe created matter, creates continuously. There is no in one moment, all the time, homogeneously in all our world, homogeneously. There is no flow from one galaxy to another one. Forget about it. Please don't try to talk about my model, because you don't know what you're talking about.
Okay, well, there's a difference. There's a difference, and at least we've clarified that. My understanding is that John's model doesn't talk about this singularity either. But you've actually highlighted a major difference between the womb model and the STOE, which I'm not surprised about. And I think we'll have perhaps more opportunity over the next few weeks to delve into that further. But I'd just like to see, does Denny have any, his camera's off. Denny, do you have any brief words you'd like to give us?
Yeah, I'd like to hear more about your what you were talking about earlier, things arriving at different times and so on.
My point, yeah.
Yeah.
And I think I need to go into that in a bit more detail, maybe on a one-to-one basis, but perhaps also not keeping it from anybody. I have raised this on a number of occasions, and it hasn't received very much attention. In fact, I was at a lecture some years ago here, given by some British astronomer, I think, a young man doing research. And I just put this to him. Now, I think he got the point, but his mouth was just open. There was no answer to it. He didn't say, "You're totally wrong, sir," or "You're right." Actually, do you have Al Kelly's books, his book rather, Denny, Challenging Modern Physics?
Yes, I do.
Well, if you read the chapter on, I think it might be called Wither Galaxies. If you read that chapter, his ideas are essentially the same as mine.
I see.
I think he even tried to model a type of globular system which perhaps was revolving. You know, it didn't have to be revolving very quickly, but the point is that we're looking at an object which is maybe thousands of light years away, so that whatever we're looking at present happens to be representative of what was there. Say you're a certain number of light years away, say it's 1,000 light years away. Well, what you're looking at is what the system was like 1,000 years ago.
Yeah.
Now, but parts of the galaxy might be 1,500 light years away. Part of it might be 500 light years away. So you're looking, admittedly now, but you're looking at what the galaxy represented at different times. You're not looking at one object at any specific time.
Yes.
Do you follow that? So,
Yeah.
so therefore, what Kelly attempted to show, I think you'd have to simulate this on a computer with computer graphics. But he said that if you have this system, which is maybe moving about 2 axes or maybe 3 axes relative to us, it would appear to have spiral arms. He says the spiral arms are not real at all.
Oh.
Yeah, believe it or not. And I just say that all these shapes are apparent. I wouldn't even go into it. Spiral arms, elliptical galaxies. I say maybe they're all the same. But, you know, so that's something that I know would be at variance with John's model. And I dare it's at variance with Vladimir's model as well. But it's at variance with the standard model, certainly. But it's something that hasn't been addressed. I mean,
no, I've never heard of that.
Yeah. Anyway, the important thing is you grasp the central idea, whether we're right or wrong, because sometimes it's hard to get people to. Yeah. So, so I think Harry wants to come back, Denny. So.
Okay. All right.
Oh, okay. So we'll leave you for the moment. I think this might be the last opportunity we have. But we have 2 more talks coming over the next 4 weeks or whatever, so don't worry about it. Thanks, Danny, for giving me the opportunity to expressing my own idiosyncrasy. Harry, any last observations? There will be a time over the next 2 lectures, but any last observations for today?
Well, I have a lot of questions. That's why I want to see if we can get a Zoom discussion group going to talk about these issues. And can we do that? Yeah. And does anybody want to do that and participate? And can we set up a time?
I'd be very happy. We've had some talks, we've had some correspondence on this, but you know, it's hard to get anybody to do it. Somebody has to set up the call, and I think it appeared to be more complicated than it is. It's actually quite simple to do.
Well, I don't think it's that complicated. If you want, I can do it. If people are interested, I don't know.
I wouldn't have a Zoom meeting.
So I'm not sure exactly. I know that Roger Anderton was trying to set up some Zoom meetings, and there's not a lot of interest in that. So I don't know if this topic might be more of a topic people are interested in. We originally, last couple of years, sorry.
For my part, if I may be bold enough to say, I think certain people are most suited for certain things. Like for example, luckily people think I'm reasonably competent to doing this sort of thing. I hope I am, and I remain so. But I think for a sort of a discussion about these technical theories and the differences between them and how they relate to other work that's gone on, I think Harry would be an ideal person to do that. And that's why in some of the emails we said, look, why don't you do it, Harry? Set that up. Maybe send a note out as to what time would be suitable and so on. But I think Harry would be an ideal person to do that. So maybe we can continue those emails offline, and if John
the main
would
problem I have is the main problem is coming up with a list of people who would be interested. That's the main issue.
Okay.
I don't want to send out an email to everybody and say, come join our meeting, unless they're interested.
Well, you know the group of maybe half a dozen people that we sort of
right,
discuss.
I'll sort of see if I can add John to the list.
Yeah,
and I have Vladimir's email. I'll come up with a list if I can.
Yeah. Okay, so Jim has just said he's interested. I think most of that list would be interested. And it's just a question of time. And if John, I know, John, you were a bit cautious about your availability, but we're very glad that you came today. We would have been a bit groping in the dark rather. So if you can come to the next two sessions, that would be great as well. But we won't hold you to it. We'd just be very happy if you could.
Okay.
Yeah. So thanks very much. So thanks, Harry, for that suggestion. And let me see now. So it devolves upon me, John, to finish the meeting, to conclude it. Is there anything brief you'd like to say before I do that?
Oh, only to thank you for this time.
Okay. Well, my part of my closing remarks will be to thank you. So thank you very much. I'll bring it down now. Yeah. So as we come up to the time allotted to us, unfortunately, we must terminate the session. And it's a good sign that we'd be very happy to continue on for another half hour or for another hour. The comments are still, James said, "Oh, John, your website, put that in the chat, maybe." I don't know if Googling STOE would get it. So if you put that in, that would be great. We look forward to having John. Would you say they accept the Big Bang concept of the redshift? It's going back to the redshift thing. We'll discuss that in more detail during the next two sessions. And I'd like to thank all of you for your participation and indeed for all your questions, and which are still coming in, but we've no time to deal with them now. We'll deal with them the next time. And also for your valued contributions, in particular, Vladimir, Harry, James, and Dennis. So, and of course, most importantly, last but not least, as we say, to John himself, because John was a bit uncertain, I think, in some of my correspondence some time ago. But I think it was more that he had these videos recorded already. So the 3 videos on the questions that we were hoping to have answered and his theory described are actually beautifully presented in a video. And I think you will all agree that the video we had today was very, very concisely expressed, and the visual aids were quite adequate. And we're hoping to see more of that in the next 2 presentations. So the thanks of the CNPS go primarily to John for having taken the trouble to have produced those 3 videos and for allowing us to present them, and indeed to boot for being here to aid me in answering many of those questions. Olber's paradox, that's another point. We'll deal with them maybe the next time. So as it's coming up to the hour now, I thank you all. I'll wish you all a very good day, whatever part of the world you're in, whether you have much of the day to arrange things or whether it's coming towards evening time, or whether it's still in the midday. So I look forward to the next session. We'll announce it, and David DeHilser will put it up and so on. So please keep a note on the announcement for John's next session, which will be provisionally. I always say provisionally because we never know for certain, but I think it'll be the case in 2 weeks' time. So I'll wish you all a very good day, and I'll stop the recording now.